Hi, I still miss you. Okay, so we're going to start today with alternating series. And alternating series bounce back and forth between the positive and the negative. And remember that in general, knowing that the limit of the terms or the limit of the sequence is 0, that doesn't tell us much about the convergence of the series. But if it's alternating back and forth and also getting closer to 0, then believe it or not, that alternating series must converge. This is called either the alternating series test or the Leibniz test for alternating series. It is important that you remember both of those terms for the AP exam because you will not be able to look them up. So you need to remember this entire blurb in front of you. So if a sub n is larger than 0, or let a sub n be larger than zeros, then the alternating series, as is stated in front of you, the alternating series converges if the following two conditions are met. The limit of the terms must approach 0, and always, the next term will always be less than the previous term, that is without the sign, for all n. So I'm going to write some stuff down real quick. You might notice a difference in verbiage here. You will notice that I'm referring to it as the absolute value of the next term. It's just less clunky to say the term without the flipping sign, because you're not taking into consideration the sign right there. In other words, a series converges if its terms alternate in sign, decrease in magnitude, which is that absolute value piece again, and have a limit of 0. Note, this does not say that if the limit of the terms is different than 0, the series diverges. That hasn't been said. It only says that if these three conditions are met, then that series converges. In order to prove that it actually diverges, you need to use a different test, and it would, I think, always be the nth term test. I can't think of an example when it wouldn't be the nth term test. Okay, so be careful with your justifications there. I repeated that little box on this page because it is so important. It is so important and people tend to forget it. This does not say that if the limit of the terms as n approaches n approaches infinity is different than 0, that does not mean that the series diverges. The series diverges by the nth term test, not by the alternating series test. Oops, I did my pen wrong. There we go. Okay. Moving onward. Okie dokie, straight out of the chute. We look at our individual terms and we see that our individual terms have a limit of 1/2. We look at the individual terms without the sign, right? Because we already know that it is in fact it satisfies that first piece of the alternating series test. It does alternate in sign. And as far as the second piece, we can see that they do decrease in magnitude, but immediately we also see that it does not have a limit of 0. So instead, on this one, we need to say that the series diverges by the nth test for divergence. So I was thinking, you might be wondering how I know that the terms decrease in magnitude. We'll just try plugging some terms in. 1 is our first term. I'm talking about without the sign. And then if we plug in 2, we have 2 over 3. That's smaller in magnitude. Then go down one more, we have 3 over 5. That's smaller in magnitude, etc. So I just kind of plug those numbers in my head. Here we see that there is an alternating sign, so it has satisfied the first condition. We also see that the terms have a limit of the individual terms have I'm sorry, I'm having trouble talking. The limit of the individual terms is approaching zero as n approaches infinity. We also now need to look at a sub n plus 1 and decide whether or not it's smaller than a sub n. Well, let's go ahead and try n plus 1 in our sequence. So we've got 1 over n plus 1 squared. Well, that's always going to be smaller than 1 over n squared. And that will be true for all n an element of the integers. I feel like that is a notation you've seen much, if at all, so I thought I would go ahead and write that down for you, that j actually means a set of integers, and it needs that double thing there. So this is going to be true. At this point, we can conclude that this entire series, n equals 1 to infinity, of negative 1 to the nth over n squared, that in fact does converge by the alternating series test. So I hope you guys are doing okay. I need to clear up your blend a lot because I feel like there are too many resources for you to study and I don't want you to get too overwhelmed. I'm going to try to pick out the best ones. I've been busy curating a whole bunch for you, but not posting them on Blend because I don't want you to freak out yet. That would be awful. I have about 50. That would be too much. Okay, time to turn the page. The verbiage associated with this page is super complicated, correct? Okay. So if you look, it says that the series is absolutely convergent if the absolute value of the terms also converges, and it's conditionally convergent if the series converges, the alternating series converges, but the absolute value of those terms, the series of the absolute value of those terms, diverges. So you will definitely need to know this. I've seen it on most AP exams. So make sure you get that verbiage down, even though it's a little odd. There are a few things you should notice or should be able to notice with practice almost immediately. You can see almost immediately that the limit of the sequence is actually 0. But you should also see that without that alternating bit, without that bouncing back and forth, that series actually, oh, I forgot words. That particular piece without the negative 1, that diverges because p is between 0 and 1. Okay, so because you can say that the limit approaches 0, you can see in the problem that's alternating, and you see that the terms decrease in magnitude, but that is not true if you were to take the absolute value of that series. It diverges there, then you can say that the series is conditionally convergent. Now, I want to point out that at no point did I say number 1, check, number 2, check, number 3, check. I didn't write that down. I did not communicate that, right? But somewhere on this page, there needs to be, or on your work, there needs to be some sort of reference to the limit. There needs to be some sort of reference to the decreasing magnitude. And at some point, you need to examine the series without the flipping sign. I know I'm using very technical language there. It's so highbrow. Okay. And here you go. You go ahead and examine your alternating harmonic series. I assume you can read. There are some magical things that come out of some of these series. In this particular case, the harmonic series actually converges to the alternating harmonic series, is conditionally convergent and can be shown to have a sum of the natural log of 2. So that's kind of fun to read over, and I would recommend looking over it. If you have questions, ask me, because this is probably one of those things that you're going to need to know off the top of your head. Eventually, they're just going to ask you a lot of questions surrounding things that they assume that you know by memory, and some of them are going to be around some series patterns that you should have memorized going into the AP exam, whether it would have been this year or next year or last year. Now we look at the alternating series remainder. Starting with this lesson, we start looking more seriously at things like remainder and error, how far you are off in your estimate once you start estimating using series. So we start with this series n equals 1 to infinity of -1 to the n plus 1 divided by n factorial. Okay, what you see here is you see the first 1, 2, 3, 4, 5 terms in the sequence. Then on the next line, so that was right. Sorry, guys. There. That was the sequence. Then I went down to the next step and added, and I got 1, 2, 3, 4, 5. I always go one beyond in that step, and you're about to see why. Okay, so as you can see, I went one beyond. If you really read the definition well, which most of you did not, because we aren't used to reading math, you would have noticed that the absolute value of the first omitted or truncated term, let me read the whole thing again because I feel like I lost words. If a series has terms that are alternating, decreasing in magnitude, and have a limit of 0, then the series converges so that it has a sum S. If the sum S is approximated by the nth partial sum, then the error is always going to be less than the absolute value of the first omitted or truncated term. In other words, if the 3 conditions are met, you can approximate the sum of the series by using the nth partial sum S sub n, and your error will be bounded by the absolute value of the first truncated term. What are they referring to, the 3 conditions met? They are referring to, again, the alternating, decreasing in magnitude, and having a limit of 0. In this particular case, we can say that the terms decrease in magnitude, have a limit of 0, and the error is less than the absolute value of the first omitted term or truncated term, which happens to be 1 over 120. Well, 1 over 120, or 1/120th, is in fact less than 1 over 100. We could also say that our error has to be less than 1/100th. All of this information allows us to move on to C, and we can use the term that we were able to go up to the fourth term, which is 0.625, and we can go on either side of it, figuring out precisely where our actual sum is. Our actual eventual sum of the series has to be between 600, wait, I can't say it, 0.617 or 617 thousandths. Oh my gosh, I need to go back to school, you guys. My brain. Or it has to be somewhere between 617 thousandths and 633 thousandths. So we do the math to find the first one, two, I forgot to make that a number. 1, 2, 3, 4, 5 terms in the sequence. And then we're going to find the first 4 terms in the series, or maybe less. We shall see. But I went as far out as I thought was reasonable to figure out when the actual sum might be less than the error of the sum would be less than 1/1000. I forgot the TH. No, I didn't forget the TH. I just don't know how to talk. Okay, now you can see how the terms bounce back and forth. You can see how their sums bounce back and forth. You can see that it's getting closer. It is getting closer and zooming in on a particular number. That number might be 9,355 10,000ths, and it might be something else. We don't really know for sure. But we have a whopping total of a whole wait, I can't even count. 1, 2, 3, 4, 5, 6 terms. And that 6th term is actually within 1/1296. So that gives us our upper bound. That is already smaller than what we want. That error is smaller than what we want, which is 1/1000th. So let's go look at that real quick. We also need to state that it actually qualifies for the alternating series test. So I'm going to write that down real quick too. Okay, so we can simply state that the terms of the series are alternating, decreasing in magnitude, and have a limit of 0. In this particular case, we don't need to prove that. We can say that the absolute value of the error is less than the absolute value of -1/1296. And we also know that 1/1296 is less than 1/1000th. Therefore, only 5 terms are needed for the error to be less than 1/1000th. And that is all, folks. I hope y'all are having a nice, restful time. I hope that things aren't too stressful. I know that this has been a steep learning curve for all of us. You can do this. I believe in you, and I will talk to you soon.